my scenario is I'll be, I guess, a lecturer from Georgia Tech, and I'll be talking to a group of engineers and engineering students about a brand new technique known as the Smith chart, which most of them should already understand by now. If they don't, then that's why they're looking at these up. So y'all are all pretty intelligent. If there's any words involved that you don't understand, just assume that you would. Say, oh yeah, that makes sense.
Right.
Okay. If you take an EMAG, it shouldn't be too far away. Oh, they will?
Please, we're running short of time. I know you want them to be able to start.
Yes. Good morning. My name is Scott Wilkinson. I'm with the Georgia Institute of Technology's Electrical Engineering Department. I'm here to teach you about a new process, a new tool that makes working with transmission lines so much easier. It changes hard algebra into simple geometrical problems. Now, many of you have probably encountered such a problem as this before, where you're given a transmission line with a characteristic impedance, Z sub 0, that you know, an unknown impedance, which is the blue here, terminates this transmission line. You don't know what this is. You need to find it out. All you know about it is its reflection coefficient, rho. Now, normally you would be able to figure this out, and it would involve a lot of tedious calculations that would only be easy to do on a computer. If you're out in the field, you're not going to have a computer. So, with this process, all you'll need are these three tools: a Smith chart, which you should all have in your possession right now, a simple compass. This cost me $1.29 at the Georgia Tech bookstore. You don't need anything more sophisticated than this. And a ruler. I think it cost about 25 cents if you get one of those brown ones. I only bought this one because you can see through. Okay, now, there are 4 simple steps, very simple steps, no major algebra involved at all, for discovering what this unknown impedance is. Now, first of all, step 0. I'm not really counting this as a step because you'll have this given to you already. You'll be given Z sub 0. It is a positive real number, which will usually happen for transmission lines. I've never seen it not happen for a transmission line, although it is theoretically possible. Rho will be of the form x plus jy, where j is the square root of -1. In other words, this is the real component, and that is the imaginary component of your rho. Now, the first step that you need to do, which is the only one that involves mathematics of a higher order than multiplication, is convert rho to a phasor form. This is the equivalent of changing it into polar coordinates, where the magnitude is of the form x squared plus y squared square root. The angle is of the form inverse tangent y over x. That's the hardest calculation you're going to have to do the entire time you're here, and that can be done on almost any calculator. Second step, plot your phasor on the Smith chart. You don't know how to do this yet. It's something I'm going to show you in just a second, but I want to go ahead and get the steps out of the way first. 3, you'll be able to read the normalized impedance, Z sub n, directly off of the Smith chart. This cuts down amazingly. Your Z will just be Z sub 0, the characteristic impedance of your line, times Z sub n. Simple multiplication. Notice that nowhere were any exponentials used, no higher mathematics than this tan -1. Now, the Smith chart you need to be familiar with. You'll be seeing this a lot in the next couple of years. You have one in front of you. I've highlighted the major portions here on this overhead that I have. Now, one of the most important things is the scale down here at the bottom. Be sure you have the correct scale. This one, if you'll notice on the side, says transmission coefficient. This is for measuring your magnitude. The magnitude that you got when you squared x squared plus y squared, took the square root. Notice it goes from 0 to 2. 2 is the highest number you'll ever get. You'll very, very rarely get 2. Now, the origin on your Smith chart is the red dot here in the middle, labeled 1.0. The origin is not 0. It is 1.0. Okay, your angle from your tan -1, the hardest calculation you made so far, is this yellow circle around the outside. Be sure to use the correct numbers. Notice that on the outside of this circle is the angle of the reflection coefficient. That is what you need. On the inside is the angle of the transmission coefficient. That is not what you need. Don't use that one, you'll get a wrong number. So for example, if you were using a certain angle, you would look on the outside, notice it's labeled positive over here, negative over here, just like your calculator will give it to you when you plug in tan negative 1. You don't even have to add 360 or subtract anything. Works out just great. Now, the blue lines here are the real lines on the chart. Any circle that goes in this direction, there are lots of them going all the way out, are real numbers. Any circle going the other direction, the green on this chart, are imaginary numbers. These are used when you read your Z sub n normalized impedance off of the chart. You'll look for a real number on a circle going in this direction, an imaginary number on a green circle or curve going in the other direction. Be sure if you're reading between 2 points, you're reading the right number. These don't go the way you'd expect them to. Notice point 2 is here, point 3 is here. They don't go the other way. Point 1 is here, point 2 is here. They don't go the way you'd expect them to. And it's real easy to get confused. Also, with the negative numbers, anything curving down, also with the imaginary numbers, anything curving down is negative. All of these would be negative j times something. All of these would be positive j times something. If they didn't want to write the negatives in, it would have just taken up too much space. Now, for you to get really convinced that you know what you're doing, really quickly, I'm going to go over an example here, one that came up earlier this week when I was out working on a transmission line. In this example, step 0, I was given a row of 0.2 plus j.1. Very typical. My transmission line was given a characteristic impedance of 50. Also very typical. You'll see these quite often. Now, using your simple calculations, hardest calculations you made in the entire problem, the magnitude of rho was 0.224. The angle was 153.4 degrees. Very easy to do. Now, that had to be read on the Smith chart. Here comes the only new thing that you've seen so far. So this is the part that's going to take a little bit more time for me to show you. Here's the Smith chart. I've already done the calculations on here, but I've done them in different colors, so it shouldn't be too hard for you to follow here. 0.224 was the magnitude. Using a compass, I went down here and said, okay, 0 to 0.224. Blue line right there is a length of 0.224. Put the compass along that, drew a circle. I know it's going to be somewhere on that radius. Then I had to find the angle. My angle was 153. Starting from here, I looked around the outside. So I got to, here's 150, here's 160. Right in between, about here, is 153 degrees, 153.4 to be exact. I drew this line straight out where they intersected. This is where to read your normalized impedance Z sub n. Now's the only new thing, another new thing you've seen. To look for the real component along the lines which circle this way. The green line is the exact one you're looking for in this condition. You look right here, it's 0.65. Real easy, no calculations involved, it's right there. The imaginary is along lines curving outwards. It's on the positive, so it's a positive number. 0.2, or is this 0.15, I believe. Right along there. It's real easy to get confused. You have to make sure you know what you're doing. Positive j.15, which gave me an impedance 0.65 plus j 1.5. Multiplying by the z that I had originally, 50, I had a final answer of 32.5 plus j, 75 ohms. No higher mathematics involved, nothing involving e to the anything. It was very easy. Any questions? If there are any questions, feel free to contact the Georgia Institute of Technology Electrical Engineering Department. We play with this stuff all the time, and we just love telling people about it. Thank you very much. Decision makers. A middle-sized firm which makes industrial ice makers. It sounds a whole lot like the job that I had this summer. In fact, the events are true, but names have been changed to protect the innocent. And they're going to have to decide between the two choices. If you want to, I can tell you later what they decide. It's already been made. Our decision's already been made.
Good, okay. Whenever you're ready, then.
Good morning, I'm Scott Wilkinson. I'm with the engineering department. As most of you know, our machines for years, since our inception 10 years ago, have been using cam timers such as the one in this device right here in all of our ice making machines and in our poultry chillers. This is a cam timer. For those of you who haven't seen it, most of you have probably seen it there in all of our machines. The company which supplies us with these timers has given us the choice of switching to a programmable controller. Programmable controller is a computer device. It's digital. It can be programmed to turn switches on and off, whereas this one uses a wheel. It's analog, and it turns to turn the switches on and off. There are three factors that really need to be taken into consideration before a decision is made whether to convert or not to convert. Both types are still available. for now. We don't know about the future. First of all, cost. Second, maintenance. And third, the future. Cost, how much is it going to cost us to do either one? Maintenance, how easy is either one of them to keep up? How easy is it for it to be repaired in the field? In the future, how is each of these going to affect us as we move into the future and hopefully expand? The first factor is cost. Programmable controller is expensive, about $2,000. That's just for the unit. That does not count the equipment that we would have to buy to program the controllers or the chips that would hold the software. The chips themselves are $50 a piece. They would also buying programmable controllers would also involve retraining of all of our personnel. Our personnel is used to using a cam timer. They've been using them ever since we started making the machines. They would have to be completely retrained how to program these new controllers and how they work in the machines. Our literature would all have to be updated. All of our literature mentions cam timers, and all of our blueprints mention cam timers. Also, our control boards are laid out to hold a cam timer. We would have to change the control boards and all of the blueprints to show the new programmable controller. On the other hand, cam timer is relatively inexpensive. I have a price down here of $200. That's really a lot higher than most of them are. Most of them are more in the range of about $50. The more expensive ones do go up to about $200. They're known by our personnel. Our personnel have used them for many years. Ever since we started, they've always used cam timers. It's in all of our literature. None of our literature would have to be changed. They all currently mention cam timers as a controlling device in our machines. And maybe one of the most important factors, they're currently in all of our machines. We have over 1,000 machines in the field at this time. These machines, if we've switched to programmable controllers, would become obsolete overnight. We would no longer have the parts to be able to fix these machines, and eventually our personnel would no longer have the expertise to fix these machines. Hopefully we wouldn't have to run into that problem. Hopefully we'd be able to keep some records around of how to fix them, or we may be able to convince the people to convert their own machines over to programmable controllers. So that is something that really needs to be taken into consideration. Second factor is maintenance. A programmable controller is digital, therefore it is extremely accurate. Once you put it in and program it to turn on at a certain time, it will not shift from that time. It is accurate to 1 millisecond. It will never go off that millisecond. Also, it can be analyzed remotely. There is a machine that can be bought where the customer in the field can program their programmable controller in their machine directly into a modem. We can plug our computers directly into a modem, and immediately we can tell what's wrong with their computer. If it's a mechanical problem, we can tell them how to fix it, or we can tell them what part to send in to us. Occasionally, if it's a programming problem, it can be fixed over the phone in a minimum of time. Also, they're easy to convert. If we have a customer in the field that suddenly decides that he wants his machine to produce dry ice instead of chunk nugget ice, he sends us a chip. The chip is about this size. Federal Express doesn't cost anything. Within 3 days to a week, we can have that chip reprogrammed and sent back to them. They plug it in their machine immediately and begins producing the correct product. Also, the programmable controllers are easy to program. The numbers you want to come up, you punch right into the machine. You flip a switch 3 times for 3 seconds, and 3 seconds is programmed into it. A switch will come on in 3 seconds or turn off in 3 seconds. Only problem with programmable controllers is they cannot be fixed by on-site personnel. The engineers at the companies will not have the technical expertise to fix these if they get broken. If there's a serious problem that cannot be fixed over the phone, they will not be able to sort of tighten a screw or flip a switch and fix the controller. Cam timers, on the other hand, are very difficult to set accurately. They involve wheels with raised lumps on them that turn switches on and off. In order to get them accurate to a second, it involves extensive turning it one way, letting it go through the program, seeing if it comes on at the right time, turning it again, letting it go through. It takes a lot of time, and occasionally these wheels do come loose and become inaccurate in the field. Secondly, the entire assembly must be removed for analysis. If there's a problem with the cam timer, you have to take the entire thing out of the machine and analyze every part of it. There's no way to plug something into it and have it tell you what's wrong. Third, the entire assembly must be replaced for conversion. If the customer decides they want a different product to come out of their machine, they have to take the entire assembly out. As you can see, it's a pretty large assembly. It has to come out and be shipped to us. We have to completely rebuild it and refit it to their machine. And last, it's easy, and this is a good benefit for cam timers. They are easily understood by on-site personnel. If there's a problem with a cam timer, in most cases, it involves tightening a screw or turning a wheel. Most engineers will be able to understand that. Even some basic mechanics will be able to understand exactly what to do there. The final and probably most important factor is how these are going to affect our future. Programmable controller is more modern. This may not sound like a very big they're going to look at us favorably. Second, there are accessories that can go with a programmable controller, but you cannot get for a cam timer. The ones that are available right now include a computer interface. Like I was saying, they can program right into it over the phone. We'll be able to see exactly what's wrong with their computer, with their programmable controller. Also, when we're testing the machines, we can plug an IBM PC, which is the only computer right now that is made interface equipment, directly into our machines. The schematics for the machine will come up right on the screen. We can see if everything's going right, what time switches are coming on, if the cycles are coming on at the right time, right on the screen. Another accessory that is out right now is a graphic program display and printout, where the program that's in the computer can be printed up onto a screen, can be printed out, sent to the person. They can see exactly what their machine is going to be doing. Also, there's more to come. Companies in Japan and America are right now working on other accessories that can be plugged into these programmable controllers. We're not sure exactly what they're working on, that's secret, but it's obviously going to be something that cannot be used with a cam timer. These things are digital, they will interface with most machines. Also, there's room for future additions on a programmable controller. We won't be using every terminal on the programmable controller. If in the future we decide that we want chunk eyes to be cut in 2 directions instead of 1, that would involve an extra stage. If we decide to put an extra stage in there, we have an extra terminal. We can set another timer inside a programmable controller, and it would work perfectly. A cam timer, you can't do that on. With a cam timer, we are in danger of becoming obsolete. Other companies have switched. Some companies have decided to stay with cam timers just because they are easy to understand and they cost a whole lot less. However, in the future, there is a possibility that suppliers will no longer make cam timers because they can't be interfaced with other machines. Also, any additions to a machine using cam timers involves adding more bulk. If you want to add another phase to your machine cycle, you're going to have to add another one of these. As you can see, that's very large. It's going to involve adding a lot of extras, having to find some place to make extra space on your control panel. These are a lot larger. Only thing you have to do with the programmable controller is add an extra wire. In conclusion, this is a decision that has to be made because if we're going to switch to programmable controllers, it needs to be done now so we have less machines in the field that are obsolete and no longer work with our literature. We need to go ahead and start making the conversion. If we decide not to, we need to go ahead and be able to tell our customers that we will be sticking with cam timers ad infinitum. They won't have to worry about their machines becoming obsolete. There are 3 factors that must be taken into consideration. Programmable controller is much more expensive. The cost is a big factor. It would also cost us a lot in terms of man hours retraining our personnel. However, in terms of maintenance and the future, programmable controllers do have an edge over cam timers. Any questions? Yes.
The cost on it, you're talking about well in excess of $2 million.
2,000.
I thought there were 1,000 machines.
There's over 1,000 machines out there. The cost of each programmable controller is about $2,000.
With the benefits we get from the new machine, will it show up on the balance sheet that our stockholders can look at?
Well, one thing you need to consider is that $2,000 is only about 5% of the resale value of one of our machines. Our machines sell for between $100,000 and $200,000. This 5% does not seem like a whole lot when you're looking at the overall cost. Other companies that have switched to programmable controllers have not seen a significant decrease in sales because of the benefits that are possible from a programmable controller. Yes?
You're saying that the people that buy our machines will probably spend less time programming their machines and making sure they have exactly what they want from the digital programmable controller as opposed to the cam timer?
We would program the machines for them. That's our job. We're responsible for making sure that the program works. However, it would take a lot less time for our engineers to program the machines to be able to get more of them out. Plus the fact that since the program is on a chip, we can have several of them already made and be able to flip them right into a machine as soon as it's built. It would take a lot less time rather than having to take each one of these cam timers and set it exactly right. Any more questions? Thank you for your time. If you have any more questions, contact the engineering department. We've studied this problem extensively for the last couple of months. Thank you very much. Oh, yeah.
Oh, well, we have systems 758, various ones.
Don't move around much.
Just
I got you
I
right.
think it's certainly that we can get the companies.
Richard, you finally did the right speech at the right time.
Most likely, most likely. It was dark. Pardon?
My scenario, real strange, y'all are managers. No. I'll be with quality control, and y'all are engineers and managers. I had to put engineers in there because we got to get some engineers, equal time. And you'll find out about the problem and why both engineers and managers need to know about it. And we're a company that makes logic circuits and boards for digital systems. Okay. Not nearly as colorful as the next one. Good morning. I'm Scott Wilkinson. I'm with Quality Control. We discovered a severe problem in our logic board manufacturing process, in that we consider 3% of our boards being faulty as an acceptable limit. That's because we don't control the chips that go into them. We don't control the wiring, and occasionally a mistake is going to be made because we do have humans building these boards. 1 year ago, we were at 1.2%. That's wonderful. That's what we like to keep it at. For a couple of years, we kept it at 1.2%, which means that our profits were doing wonderfully. However, last year, we hit 12%. That's 4 times what we consider acceptable. As of yet, we haven't gone into the red yet, but if we keep it 12%, we will be severely in debt by the next couple of years. One of the most telling factors to look at is the percent rejected versus the number we're producing. Because of a government contract, we started producing a whole lot more than we've ever produced in the past. Last June, we were at about 1.5%. That's how many we were rejecting. This is the percentage rejected. This is the number we were producing. We were producing about 2,000 per day. If you'll notice, these curves walk almost exactly alike. As we produced more, the number we rejected went up. As of last month, we were producing almost 20,000 boards per day. We were also rejecting almost 12% per day. That's a whole lot of boards. When you're rejecting only 1 or 2% of 20,000, that's still a lot of boards, but it's not nearly as many as when you think of 12% of 20,000 boards. That's a whole lot. Each of these boards is costing us about $2 a piece. We usually sell them for about $20 a piece. So as I said, we're not into the black. We're not into the red yet, but if that keeps up, we'll be into the red by next year probably. Putting those factors directly against each other, the percent rejected versus the number produced, it's a definite upward trend. Well, back when we were producing 1 or 2,000, we bounced around a bit. We stayed around 2, 3%, which is what we considered acceptable. Only recently we've been producing up into the 20,000 range. You see, if you'll notice, as soon as we started producing up into that range, we immediately went into 12%, 9%. We first passed 3% at around 6,000, around 7,000. At that point, we knew we had a problem. We thought it may go back down. It didn't. It went up to 12%. If this trend continues, we could be up to 20%, which is well beyond anything we could ever accept. The main cause, we believe, is that we're using multiplexer logic right now. We don't think that our problem is with our workers. They're trained well. They're conscientious. They know that if they make mistakes, they won't be around for very long. So we think the problem is with the logic we're using, the multiplexer logic. The number of percent of rejections due to shorts is at 87%. Obviously, this is the major reason we're having a problem. There are shorts in our boards because we believe that because of the logic we're using, the multiplexer logic. With the multiplexer, those of you who aren't familiar, the total number of possible connections per chip is 16. There are 16 pins, 16 wires have to be connected. However, not all these wires have to be used. Usually we use only 15 of them. However, of these 15, 9 of those pins are connected to either positive power or negative ground. If there's ever a connection between power and ground, that's what we consider a short. That is when the board is considered faulty. At times it causes severe damage. Boards that have connections between power and ground directly will be rejected. With multiplexers, there are 9 possible times that this problem could occur. Right now, the main reason we have such incredible production is because of the government contract. We believe that we're catching all of the mistakes before they get out of here. If the government begins to suspect that we can't catch all these mistakes, 12% rejection ratio, it's very obvious, it's very possible that some of them are getting through. That's a lot of faulty boards. If some of these start getting through, the government thinks that we are selling them a defective product, they will cancel. They have told us they will cancel. At that point, we will lose about 90% of our business. There's also a possibility that no one will come to us anymore. We'll be seen as the producer of a faulty product. In the future, this would cause not only our profits to fall, but it would cause our business to drop off and no new business to come in, which could lead to the death of our company, or at least this division of our company. Are there any questions?
How do you think the logic, what logic, is it design logic or is it the logic of the multiplexer or what?
The design logic using the multiplexer, because of the way a multiplexer works, there is inherently a large number of connections to positive and ground. Because of this large connection, is inherently a large possibility of people connecting positive to the wrong place or shorting between a positive and a negative wire.
So that would be the human factor then. It's just that we're forcing them to do something that could be very, very difficult.
We believe there are other possibilities though, because there are several different kinds of logic that are available, different kinds of chips that are available that will do the same thing. We believe that because we're using the multiplexer, that's the reason that we're having these problems.
And so we were switched to a different type of logic that wouldn't be near as many connections between the plus and minus.
We haven't looked at the solution yet. That's one of the possible solutions. Any more questions?
What percentage of the boards do we test? Do we test every single one?
We test every third board right at this moment. Because it's a government contract, we don't want to have any chances. But at 12%, evidently we need to start testing all of them. One of them's going to get out there. Any more questions? Thank you.
Are testing all of them?
That's all I'm doing.
Got your tape? Use this one? I got one in there. It's mine. Mine? No problem. I've always wanted to record this. I got it. Today we'll do recording by handheld camera.
Today's speech sponsor.
Hey, that sounds like a great idea. I think we'll be ready to do that by the end of this year.
Where I went to college, one fraternity would throw a used piano off their roof once every year. There'd be a big party afterwards, and you would smash the piano.
Great picture here.
It's kind of like driving a car off a cliff at that point. Where's the...
Show this from a different angle. We'll have the camera pointing towards the audience. See how they react to your speech.
Pardon now?
Try from a different angle, have the camera pointing towards the audience and see how they react to the
Audience
speech.
reaction was...
During this speech, the audience seems
All right, let's go. Or pick somebody else.
No.
You might get an extra memo.
Did you tape in already?
Yeah, that's this guy.
It's must don't worry about it.
Get so caught up in Oh, I'm sorry. I thought you were doing something else. My scenario, if y'all remember, it was really impressive that you remember, I know. It was something about, remember the logic boards that were going from 1.2% to being rejected to 12%? Well, that was the problem, and I'll reiterate that in a minute. From quality control, it's a very small, very informal firm, and as you can tell, because I forgot my shoes today. Very informal firm. And y'all are managers and engineers. I like your shoes too. You got a nice close-up shot on. Good morning. I'm Scott Wilkinson. I'm here from Quality Control, for those of you who don't know me. I came and spoke to you last week about a problem that we discovered in our logic board manufacturing department, and that we consider an acceptable percentage of rejections 3%. A year ago we were at 1.2%, and just recently we've gone up to 12%, which we consider way beyond acceptable. We decided through research that the problem was as a result of the multiplexer logic in the boards. So after research, we decided the best solution is to switch from multiplexer logic to direct logic using NANDs and NORs. Those of you who don't know what NANDs and NORs are, they're like ANDs. If you've ever used logic tables, an AND is a certain kind of logic, and OR is also. NANDs and NORs are the opposite of that. They're cheaper to buy than ANDs and ORs, and they're just as easy to use. There's quite a few advantages to this problem, to this solution. Some advantages that don't even relate to the problem that we discovered as we were researching it. I don't know why we haven't switched to it a long time ago, actually. The first advantage is that, first of all, I'm going to move this out of the way. First advantage is that on an average there's only 4 connections to power or ground per chip, whereas with the multiplexers there were 9. We figured that was the reason there were so many problems. There were shorts between power and ground. Of these 4 connections, 2 of them are going to consistently be going to the same pin. Every chip has to have 1 power and 1 ground. So those 2 we shouldn't have any problem with. The other 2 are at various places with only 4 out of 16 pins. We don't think there'll be a problem with shorts. Secondly, the redesign of the board spreads out the location of these connections. Whereas before all the connections were on 1 chip, which is about this size if you've ever seen one. I'm sorry I couldn't bring one in today. All the connections were taking place in a very small area. There's a great chance that solder or pieces of metal or any sort of short could occur between any of the 2 pins. Using the redesign, we're going to be using several chips instead of just the 1 chip. They'll be spread out. It'll be easier for the workers to see exactly what they're doing. Third, it's easier to read the design equations directly from the layout. This is something that should have been thought of a long time ago. With multiplexers, if you look at a board, you won't be able to tell what the equation is. It's very difficult to be able to figure out. You have to trace where everything comes from, write it out, and then find the equations. You have to know exactly how the multiplexer works to be able to do this. With NANDs and NORs, you'll be able to read the equations directly off of the board. Any debugging that has to be done, an engineer will be able to look directly at the board and figure out exactly what's wrong. This is something that should have been thought of a long time ago. Would have saved us a lot of money in the long run. Fourth, conversely, it's easier to design the layout from the equations. A designer can use something called mixed logic. Those of you who don't know what mixed logic is, it's a very simple process, whereas an equation is converted directly into hardware on paper in several easy steps. No equations have to be manipulated so that they'll fit onto a multiplexer. They fit right directly into the chips. We'll be able to look at a design and say how much it costs. A whole lot easier. We'll be able to say, well, how many multiplexers is this going to take? We'll be able to tell immediately how many NANDs and NORs it's going to take and how many chips it's going to take, and therefore how much it's going to cost. Lastly, the cost of the new design is about the same on the average. We took several of our boards, took the equations off of them, used mixed logic, converted them to direct logic using NANDs and NORs to see how much they would cost. Only a few cost more. As a general rule, they cost less. Now, multiplexer, for those of you who don't know, costs about 3 times as much as a NAND or a NOR chip. On the average, we used about 3 times as many chips per design. So there's no problem with the amount of money. We would not be losing any money by switching to this design. We did check, however, several other alternate solutions for people who we figured would be asking questions. First alternate solution we checked is to reduce the number of boards produced. As I mentioned in my last speech to you, the number of faulty boards we had increased incredibly once we started producing a whole lot of boards. So therefore, it seems logical that if we produce a less amount of boards, we'd have less rejection. However, very obviously, we would have to drop contracts. We wouldn't be able to fulfill contracts anymore. The first one we'd probably lose would be our government contract, which right now, 90% of our business. We lose the contract, we lose the profits. Secondly, loss of income permanently. Once we lose these contracts, they won't come back to us. We tell the government we cannot produce what they need, they're not going to come back to us later and ask, well, can you produce it now? And lastly, there's no way to expand. If we restrict ourselves to a certain number of boards that we're being produced in this department, we'll never increase, we'll never grow, and a company that doesn't grow will die. Second alternative solution is to hire more employees. It was suggested that if we have more employees, they'll have less connections per employee to work with. Therefore, they would make less mistakes. However, when we looked at it closely, we saw that it would not correct the inherent flaw in logic. The other advantages that we came up with, and that you can read directly off of the board, would not be correct. These problems were problems that will eventually come up, and when a large amount of designs have to be produced quickly, multiplexers slow us down. It's something we hadn't thought of before that we suddenly realized is a great advantage with NAND and NOR logic. Another problem with hiring more employees is that it costs too much, especially in the long run. If you hire an employee, you're going to have to start paying pensions for these employees. It will require benefits as well as salary. Comparing to the other solution in which no cost increase was occurring, hiring more employees just is not cost efficient. Third alternate solution is to do nothing. This is not actually a solution. It's merely brought up to show you the urgency of the situation. If we do nothing, we're going to start losing contracts. We have a possibility of losing our government contract first. They will not accept a company that has a 12% rejection ratio. Secondly, once we lose these contracts, we'll start losing profits. We'll also start losing profits due to the boards that are being rejected. Something definitely has to be done. We studied the situation. We've gone over the alternate solutions. These were the 4 solutions we came up with, and our definite solution, of course, is to switch to NAND and NOR logic. As I said, it won't cost any more. It'll save us a whole lot of money in the long run. Are there any questions? Yes?
Wouldn't it be like implementing a changeover cost?
Slight cost, but the fact that we already use boards that are interchangeable, because we produce a lot of different kinds of boards. The company that gives us multiplexers right now has no problem supplying us these new chips. The only problem is that we have to tell people what they're doing now. No problem. Yes?
You mentioned that some of the advantages were extra and some directly solve the problem.
Yes.
Could you just specify which is which?
All right. Put this back up here. Solving the problem, we notice there's only 4 connections, therefore there will be less shorts. Redesign of the board spreads out the location of the connections. Again, less shorts, there'll be more space for them to work with. These 3 following, 3 at the bottom, well, except for number 5, which can be considered a result of that problem too. These 2 are extra, but bonus, wonderful things that happen if we switch over. Things that should have been thought of a long time ago. Are there any other questions? Thank you very much. Boy, I talked fast.
Sure did.
I talked fast slower when I practiced that.
Well, still 8 minutes.
Okay.
Wow.
Very close.
I just like being.
Okay. Next up is Stephen.
This guy.
All right. Sure, I used the rest of my tape.
They're due Monday
Oh, really?
by
Hey,
Angie.
put the game on my class.
It's a good idea. I don't have a VCR. I don't have a VCR.
It's on the
TV, man.
schedule. Janet?
Who's winning? State's still playing. State's fouling like crazy. State's probably losing. Maryland's gonna win.
That would be
Maryland's
silly.
going to beat NC State?